So, most suitable components for the manufacture of lenses are those in which refractive index should be high and it should be constant. So, this results in reduced chromatic aberrations. We will see what is chromatic aberrations later, but for the time being we can assume that most of the lenses and other things are all basically used to produce parallel beam of electromagnetic radiation. So, the fabrication of prisms and lenses, what we need is a high refractive index, but they should be highly frequency dependent also. So, the requirement of high frequency dependency on refractive index weighs heavily on the selection of the lenses. So, another property of electromagnetic radiation is reflection of radiation. So, I think most of you are familiar with the reflection of radiation, because every day we see ourselves in mirrors. Mirrors do the job of reflection. Whenever you see you brush your teeth, you go in front of a mirror, check your teeth, etc. It is just a reflection. Whenever you are in front of a camera, you will be seeing the reflection of yourself, or a mirror, you will see a reflection of yourself. So, the mirrors essentially represent the radiation falling on them, they reflect their radiation. So, without any loss of incident radiant power, they are since there is no radiant power loss in mirrors, they are used as optical components in a spectrum. What do we need? We need a concave mirror that reflect the radiation as well as concentrate the reflected radiation at its focal point. Now, these concave mirrors are available to you all over the world. You are very familiar with them, and the concave mirrors basically are used in most of the cars. The headlight of a car, they always you pass it through a concave mirror, so that the beam of radiation in front of the car is properly illuminated with a parallel beam. And even on the side mirror of a driver, the concave mirrors are used, because whenever you are parking, it should be visible what is available at the back. So, again you need a parallel mirror, concave mirror, which gives you a concentrated beam. And when radiation crosses an interface between the media, that means if I have a mirror, radiation passes through the mirror, differing it, there will be a difference in the refractive index. So, for a beam entering an interface, that is a glass plate or whatever it is, if it is interfacing at right angles, the fraction reflected is given by this equation. Intensity of the radiation, reflected radiation divided by the intensity of the original radiation, IR by IO, is a ratio of N2 minus N1 square divided by N2 plus N1 square, where N1 and N2 are the refractive indexes of the two media. Normally, we have air and glass as the two refractive index. I can have water and air and so many other possibilities are there, but in most of the spectroscopic instruments, we have only the air and glass or air and lens, etc. Glass is basically a transparent material on which a non-reflective coating is provided at the back. So, in such cases, the reflection rules are governed by this previous equation, this equation IR by I0 is equal to N2 minus N1 divided by N2 plus N1, both of them squared. So, this is how it looks, refraction of phenomena, and there will be light path change here, and whenever radiation passes at an angle through the interface between two media, just like what I had shown here. It is coming at an angle. It is not coming from the top, but it is coming at an angle, then it will not pass through the angle straight away. Okay. So, in such cases, extent of refraction is given by N2 by N1 basically. So, refractive indices of different materials are measured with air as one medium, and they are all available in databases for quartz, for glass, for metals, for aluminum. Like that, there will be lot of changes in the refractive index of the material. This is another property of the electromagnetic radiation that I always associated whenever electromagnetic radiation interacts with a given media. The media what we have already referred to is, it could be vacuum, it could be gas, it could be material, solid, liquid, etc., etc. Now, I am going to talk to you another property of the radiation, that is scattering of radiation. Now, what happens during scattering? Whenever, again imagine I have some amount of material, radiation is passing through that material. So, the atoms are there, ions are there, molecules are there, all these things are in a state of constant movement, constant dynamic equilibrium. So, there will be part of the radiation is absorbed by the atoms, or if the atoms are bigger, they are by the molecules they represent, and if they are still bigger, they could be particles like dust particles, or it could be liquid particles, aerosols. So many other solid and liquid particles are there. All these liquid particles and dust particles, etc., whenever they are in a given space of time and electromagnetic radiation is passing through them, there will be scattering. The light will fall on the particle, and then it will not pass, it will not follow a known path. It will be scattered in all directions. That is known as scattering. In reflection, it follows the same path in which it has gone and hit the material. In refraction, it takes comes there, takes a bent path, and then again it comes out. Whereas in scattering, part of the energy is absorbed, wavelength is changed, frequency is changed, and then it will be dispersed in all directions. So, the transmitted light will contain all kinds of radiations, and it will be in all directions. So, that is what I have written here, particles having comparable dimensions to that of the incident radiation. That means, comparable dimension to that of the incident radiation means particle size should be of the order of angstrom units. That means, they would be in the form of atoms or molecules. So, if such is the case, the emitted radiation may result in destructive interference, except those travelling in the original direction. So, a very small fraction of the radiation is transmitted at all angles, which I have already explained to you. So, scattering by molecules or aggregates having smaller dimensions than the incident radiation is known as Rayleigh scattering. There are two kinds of scattering. One is by molecules or aggregates having smaller dimension than the incident radiation, that is known as Rayleigh, and different larger molecules scatter radiation in different quantities in different directions. So, smaller ones, scattering by smaller particles is called as Rayleigh scattering. Scattering by bigger particles is known as Mie scattering, MIE, Mie is the name of the scientist. So, when the scattered radiation is quantized like those occurring in vibrational energy levels, we call it Raman scattering. That is a very well known scattering phenomena, and what Professor Raman said is the scattering occurs in a quantized fashion. So, they can be used like any spectroscopy. So, that is how it is known as Raman spectroscopy. So, Raman scattering is also part of the interaction of the electromagnetic radiation with the material. So, another property of electromagnetic radiation. So far we have discussed reflection, refraction and then scattering. Now we are discussing about polarization. So, what is polarization of a radiation? As I have already explained to you, the radiation is a bundle of electromagnetic waves moving through a given space, and that bundle is usually associated with electromagnetic radiation. So, electromagnetic radiation is if the particle is moving through like towards you, the electromagnetic radiation will be going like this and magnetic radiation will be going perpendicular to this. All the three will be going in the same direction. So, viewed on end, how does it look? So, it looks like this. So, here you can see that polarization of light, where the incident beam on the left side here. On the left side is a bundle of electric field and magnetic field. Radiation is going through this end to this end. Okay. So, from this end it has it has all the electromagnetic part and as well as the direction. Now, I put one polarizer, vertical polarizer. What it will do is it will stop all the electrical vertical field, one field. So, the outcoming radiation out of this, the electrical field is from the back side before the polarizer. There are two components, here it is only one component. Now, if I put one more component, one more polarizer here, I will have only the direction. Both electric field and magnetic field would be destroyed, they will not be there. This is known as polarization of light waves. So, that means it is separation of the electric and magnetic field from the radiation that is associated with each one. This is a very standard technique shown in almost all TV serials and other things. All they got to do is use a polarizer which will permit the movement of the electric field, cut off the electric field or magnetic field, and that is how it works. So, dispersion is again another complex phenomena. A dispersion usually occurs in two regions. One is normal dispersion, where there is gradual increase in the refractive index with increasing frequency. Anomalous dispersion occurs coinciding with natural harmonic frequency of some part of the molecule or atom or ion leading to the absorption. So, in spectroscopy, dispersion curves are important for optical components such as lenses, mirrors, etc. Again, these are very important concepts. Most suitable components for the manufacture of lenses are those in which refractive index should be very high and it should be constant. This results in reduced chromatic aberrations. For the fabrication of prisms, what we normally do is we take the, I have not shown you here, this is a prism. Okay. So, this triangular glass material, you must have seen prisms like this. So, for these prisms we use them as dispersive material devices. Radiation is coming through it here and then it will pass through this, it will have different components and each component will have different refractive index, and because of this property, they will exhibit you a white light entering at one end will give you red, orange, yellow, green on the other side of the prism. We will come back to this. What I wanted to show you is dispersion. of electromagnetic radiation, and lenses and prisms are the most important components for which high refractive dispersion characteristics are required. So, I was talking about the normal dispersion and anomalous dispersion. Normal dispersion is like this, then there is gradual change, but in anomalous this thing there is a sudden change from this point to this point. Okay. So, this point to this point there is a sudden change, and here you can see that on the left x axis I have 10 raised to 13, that is infrared, 10 raised to 14 frequency, and 10 raised to 15 is ultraviolet. So, from infrared to ultraviolet range there will be change in the refractive index. Therefore, the refractive same material what is used for infrared may not be useful for ultraviolet, and vice versa, and several other systems also. What some material useful in the infrared, a lens material, for example, if I use a glass for infrared, it will not be useful for ultraviolet. Glass also is not very useful for infrared. So, for visible light ordinary glass will be all right, because it will not have change in the normal dispersion. But if I use the same glass for ultraviolet, it will not allow any radiation to come out at all through the glass. So, a lens or a prism to be used in an ultraviolet spectrophotometry cannot be used in the infrared. So, what is useful in visible range may not be useful in the ultraviolet range. So, for each different spectroscopic technique, what we need is different materials which are suitable for the passing of the electromagnetic radiation with minimum side effects, that is normal dispersion. That is the importance of this figure. Okay. So, diffraction is another aspect of interaction of radiation with electromagnetic radiation, matter with electromagnetic radiation. So, what does diffraction refer? Diffraction refers to the bending of parallel beam of electromagnetic radiation as it passes through a sharp barrier or a narrow opening. It is a consequence of interference which can be easily demonstrated in the laboratory. What I do is I take one parallel beam of light, coming through this, through fingers like this, and then I put a small pinhole, put a screen in front of that, put a small hole in front of it like this, so that the diffraction will occur. So, whenever a parallel beam of light is allowed to pass through a small pinhole or two closely spaced pinholes, through the pinhole all the radiation will be spreading, and sometimes what happens when they are spreading through one pinhole, another pinhole may be crisscrossing the electromagnetic radiation of the other coming from other pinhole. So, the interaction of these two radiations through the pinhole represents what is known as diffraction. So, there could be constructive interference or there could be a destructive interference. Whenever there is constructive interference, high school physics, I am teaching you, constructive interference means you will see a string of bright and dark, bright spots, dark spots like that. But if there is destructive interference, you will not see any bright spot at all, you will see only the dark spot. So, if the radiation is monochromatic, again what is a monochromatic radiation? A monochromatic radiation is the radiation having one frequency, one wavelength and single amount of energy. So, it may be a bundle of radiation, but all have the same wavelength. So, whenever I take monochromatic radiation and pass it through a series of two pinholes etc., there will be a series of dark and light images which appear perpendicular to the plane of radiation. So, that is diffraction. So, here is the representation of a electromagnetic radiation. Here what I have is a radiation coming through this. There is a small pinhole here 1, 2, 3, 4 in the center, and the radiation is coming out like this. You will see bright patch, black patch, bright patch, black patch like this. As it spreads across, you will see a bright patch all in the center, black patches at the this thing. So, all the black patches represent the destructive interference, while the bright patch represents constructive interference. So, the geometrically I can say that we can see that the refractive index is a CF is given by BC into sin theta. For two beams to be in phase at D, it is necessary that they should correspond to the wavelength of the radiation, and that wavelength is given by CF here again, that is BC into sin theta, and for reinforcement can also occur at 2 lambda, 3 lambda etc., twice the wavelength, 3 times the wavelength. That is known as order of diffraction, first order diffraction, second order diffraction, like that. And in general what we have is any number of interference or diffraction, and that is given by n lambda is equal to BC sin theta. BC can be related to the crystal structure, that is 2D sin theta. N lambda is equal to 2D sin theta. This is a very important Bragg's equation. So, whenever the phase differences remain entirely constant with time, the system is said to be coherent. Then only a regular diffraction pattern is obtained. The spacing of the bands depends upon the distance between the slits, that is mechanical slits, and the resulting equation is n lambda is equal to sin theta, and if two different wavelengths are used, the two colors will be separated on the screen. So, if white light is used, a number of small rainbows colors you will be obtaining on the other side. So, by placing a moving slit across the screen, any color or wavelength can be chosen. For example, here in the next figure, if I put a plate, a mechanical plate here with an opening in this range, it will allow only red and keep all orange, yellow etc. green below, because there is only one slit and that slit will cover only the red region. Now, if I want orange, I have to move the slit downstairs a little down, and then I will be coming in the orange range. You look at the same figure again, you will still move down, you will see only the yellow color. So, the same slit can be moved up and down to get red, orange, yellow, green, blue, indigo, violet etc. So, this is the beauty of prisms and slits. So, the slits, prisms, as I need a prism as a dispersive unit, and after that I need a part as part of the instrument, I need a slit. Now, the prism basically disperses incident radiation in different colors, as you can see from this figure here, is it not? So, the radiation what amount comes out as red, how much amount comes as blue etc., it depends upon the prism material. And a prism can also be used to disperse ultraviolet, visible and infrared radiation. Therefore, prisms, lenses, concave mirrors, gratings, diffraction gratings, all these are part of the spectroscopic equipment in all equipments. So, the material of construction depends on the wavelength region. This I have already told you, that what is useful in infrared may not be useful for visible range, what is useful for visible range need not be useful for ultraviolet range, and vice versa. So, a prism I can construct like this, I can take a prism like this and choose one more prism like this and then put it on the other side, that you will get it here. That you will get a picture on the left side, that is 60° prism. That means what I have done is I take a prism on the right side, that is 30 degrees, join it opposite side, and I get what I get on the left side. So, if two 30° prisms are joined together, I get a 60° prism, and both are used in spectrophotometers. If I use two 30° prisms like the previous one, like this one 60, it becomes a 60° prism. This is known as Cornu mounting. Okay. So, in Cornu mounting I have two 30° mirrors joined together at the vertical face. But if I use only one prism like this and coat it with a mirror surface on the other side, what it does is a blue radiation you can see coming from this side, reaches the mirror surface, reflects back and then goes back. So, the distance actually travelled by a 30° mirror, the mirrored mounting is exactly same as a 60° prism. You understand the difference? Basically, a 60° is a 60° prism is one time pass. 30° prism is it goes straight and then gets reflected on the same side. So, the distance between the two would be essentially same if I mirror one side of the prism. So, the one side of the mirror prism, that is 30° prism, is known as litro mounting. So, litro mounting is collected on the same side. So, here refraction takes place twice on the same side with less material. I save the material as well as I save the space. Why? Because here I have to put a slit on the other side of this prism if I use a 60° prism, whereas if I use a 30° prism, to collect the reflected light I have to put the slit on this side only. That means the instrument becomes a very small instrument compared to a 60° prism. That is the advantage of a prism. Litro mounting and Cornu mounting. So, here I have monochromatic slits, a pictorial presentation, I have a mirror, I have concave mirror here, I have slit here, a radiation is coming through this, I have another mechanical slit, and then it gives me different kinds of wavelengths. And this is my slit, and I can move this slit at different places to collect the top ray, second ray, third ray, fourth ray, fifth ray, like that. And for longer wavelengths I can use a multi channel. I can take a single plate with multiple slits. So, it will collect one ray from here, another ray from here, and so multiple rays can be simultaneously detected instead of making the one movement from the same slit. So, that is known as multi channel detector. I need a detector here to find out what is coming out. Okay. So, we have discussed about the monochromator slits, and in the monochromator slit what I have is part of the radiation is the peak wavelength, that is lambda 2, and part of it is lambda 1, lambda 3, and here I have an exit slit, here I have a slit and effective bandwidth. So, this is radiant power. So, bandwidth monochromator setting, if I take out any radiation coming out from a monochromator slit, a bunch of radiation comes out. It is not a single wavelength, even though most of the radiations are parallel. What comes out is a pure wavelength like this in the center, but also a little bit of other radiations corresponding to different wavelengths. So, this is a practical difficulty. whenever we are talking of monochromator slits and monochromator designs. You will never get a single wavelength output from any spectroscopic device, because it is the inherent property of the slit. If you can imagine something like this, a basic radiation will be, center radiation will be the what you want, plus there will be some unwanted radiations corresponding to different wavelengths. So, that how we select that out of that is another aspect, but basically what comes out is a bunch of wavelength corresponding to the wavelength what you want, where the slit is placed exactly, but also some unwanted extra radiation having slightly plus and minus wavelength on the of what you are choosing. Okay. So, that is what we mean here, bandwidth. So, whenever we say I want 450 nanometer wavelength, what I will be getting is 400 instead of 420, I will get maximum 420, but also I will get about 415 and 425, some amount of extra radiation. So, the whole range of wavelength corresponding from 425 to 415 with maximum at 420 is known as bandwidth. So, for good spectrophotometers, what I need is a very small bandwidth, small amount of wastage. That is the importance of the slit and slit management. So, we will continue our discussion after about 5 minutes. Thank you.